Good morning, students. In last class, we have completed D block elements. In that, some important compounds. Some important compounds in D block. See, some. So you take Chromium Chloride. So formula CrO2Cl2. So in entrance examinations, direct they will ask compounds. So which of the formula is the Chromium Chloride? So like that. Some famous you write down that. So Lucas reagent. So HCl plus N-hydrous zinc chloride. So zinc is the D block element, chromium is a D block element. Next, Tollens reagent. So in the organic chemistry, this is a famous Tollens reagent. That is ammonical silver nitrate. So silver nitrate, AgNO3 solution plus so ammonium hydroxide with a little amount of NaOH combination. So simply they can tell Ag plus OH minus. So this combination we call it as a Tollens reagent. Next, Fehling's reagent. So instead of this copper will be there. So sodium potassium tartarate plus copper sulfate solution. So copper plus 2 D block element. Next this is tartarate. Simply they can write copper plus 2 and OH minus combination. Next, lunar caustic. So lunar caustic, that is AgNO3, silver nitrate, horn silver. So horn silver means AgCl. Next, amalgam. Already we discussed about amalgam. So any metal combining with mercury. So metal combining with mercury you call it as amalgam. So iron is not forming. Iron is not forming amalgam. So one important. Next, suppose you take steel. So steel is a combination of iron plus carbon. Next, permanent magnets. So permanent magnets, that is alnico, nickel, cobalt, iron with a combination. So already the mixing of metals we discussed that also. Next one, calomel. So calomel means mercurous chloride, Hg2Cl2. Next, vitriol. Some vitriols are famous. So oil of vitriol. So generally oil of vitriol means sulfuric acid. Sulfuric acid, another name oil of vitriol, their salts. So actually white vitriol, green vitriol, blue vitriol. So these three are famous. So white vitriol means zinc sulfate. with 7 water. So green vitriol, that is iron sulfate. Next, blue vitriol is copper sulfate. See, next you take a mish metal. So this is a 95% lanthanides plus iron is a 5% and some other impurities also they have. So that is one important. Next, highest density. So highest density element is iridium. After that osmium. So least density. So least density means titanium. So density least. So density least, melting point is highest. So that's why it is called as wonder metal. Next, melting point. So highest melting point is goes to tungsten. So least melting. So least melting point is mercury. So already it is melted. So liquid metal only. So that's why it is available at room temperature, liquid form only. Next, some other famous are there. So suppose Ziegler-Natta catalyst. It is also one of the famous. So Ziegler-Natta catalyst. So in the polymers it is coming. So this is the combination of AlR3, aluminium, trialkyl aluminium and titanium chloride, TiCl3 or TiCl4. So like that, so many important compounds are present in the D block elements only. Okay. So this is about our D block elements. Next, in this subtopic also there, that is the F block elements. So D and F both are one chapter only. So our next topic is F block elements. See, first of all, definition. How to tell the F block elements definition means this is depending on electronic configuration. So in the electronic configuration, the last electron, if the last electron enters into the F orbital, then they called as F block elements. See, in the electronic configuration, if the last electron enters into the D orbital means D block element. Enters into the F orbital means they are called as F block elements. So actually, where is the location in our periodic table? Suppose you see the periodic table, how it is. So this is S block elements. Next, it will come F block. Next, D block. Next, P block. So actually, this is the original periodic table. Suppose 14 F block elements you are writing means the periodic table length is increases. So that's why what they did. So now our modern periodic table is like this. See, to decrease the size of the periodic table, this F block is taken into down only. So this is S block, D block, this is P block, this is F block. See, F block contains two periods. Two periods are there, 14 groups. F block elements have two. See, this is a 4F series. 4F series, 5F series. See, 4F series you called as the lanthanides. Next, 5F series you called as actinoids. So here, general electronic configuration. So general electronic configuration is N minus 2 F 1 to 14, N minus 1 D 0 to 1, NS2. So suppose the same thing you apply for lanthanides, general electronic configuration. Here 4F 1 to 14, 5D 0 to 1, 6S2. So for actinoids also, general electronic configuration, here 5F you can take, 5F 1 to 14, next 6D 0 to 1, next 7S2. So now we will discuss what are the lanthanides and actinoids elements. See, lanthanides. So that shortcut is Seprenapus, cerium, praseodymium, neodymium, promethium, samarium, Seprenapus, Yugat badiho, europium, gadolinium, terbium, Yugat badi, dysprosium, holmium. So Seprenapus, Yugat badiho, terbium, Yertiulu, Yerbium, Thulium, Ytterbium, Lutetium. So where these are started? So atomic number first. So that means D block elements you can take. Scandium, titanium. Next, yttrium, zirconium, hafnium, lanthanum, hafnium, tantalum. So here lanthanum after elements you called as lanthanides. Suppose you want to atomic number means scandium is 21. You add 18. So that's why you are getting what? 39. 39 you add 18. So 40, 57. So lanthanum is 57. After lanthanum these are started. So these are 58, 59, 60, 61, 62, 63, 64. 67, 68, 69, 70, 71. So the atomic number 58 to 71 are called as lanthanides. So where is this location? So these are sixth period. This location is sixth period. Next, group also. Which group means they are taken as a third B. So third B, otherwise a third group. So that also, every point is also important in your entrance. Sixth period, third group. Next, from which atomic number to which atomic number. So that is also important. Next, actinoids. actinides. So the shortcut is Tapa Unpuva. So thorium, protactinium, europium, uranium, neptunium, plutonium, americium, Tapa Unpuva, cubaca, curium, berkelium, californium, einsteinium, fermium, F. manganol, mendeleenium, nobelium, lawrencium. See, all are radioactive elements only. After the uranium, all are radioactive elements only. Their scientist names only they are provided. But what is the atomic number from where to where means here actinium after 14 elements you call as actinoids. So here you add 32. So then what happens? 50, 60, 70, 80, 89. So 89 is actinium, 89 after actinoids. So 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103. So thorium 92, lawrencium 103. These elements you called as actinoids. Next, another important, these are called as F block elements, also called as rare earth elements. So these are rare earth elements except lutetium and lawrencium. Except lutetium 71 and lawrencium 103. Remaining F block elements. So remaining F block elements you called as inner transition elements. So except 12th group, D block elements you called as the transition elements, last two of F block elements, except these two, remaining all you called as inner transition. Next, in actinoids after uranium, so these all are what radioactive elements. So after uranium, the elements are called as transuranic elements. Transuranic elements are man-made elements. So transuranic are man-made elements. Next, if you see the electronic configuration in this, so here, where is the location of these also important? So location is 7th period. So in the periodic table, location they are asking means you must tell a period and group. So this is 7th period and group is 3rd B only. So lanthanides and actinides, their positions means period and group also important. Next, we are taking comparisons between these two. See, these properties are also similar to D block elements only, but less than that. So we are comparison, we will write one side lanthanides. One side lanthanides, another side actinides. So you see the comparisons. If you perfect in comparisons means this chapter will be over in this. See, from where to where? You call it as lanthanides. So that is cerium. So 58 to lutetium. So that is 71. Next, which one is actinides? Thorium 90 to lawrencium 103. So you call it as actinides. Next, what is the general electronic configuration? General electronic configuration means 4F 1 to 14, 5D 0 to 1, 6S2. Here, general electronic configuration. So here 5F 1 to 14, 6D 0 to 1, 7S2. Next, general oxidation state. So general oxidation states. So generally everybody is showing a +3. General oxidation state, lanthanides are showing +3, but some elements are showing +2 and +4 also. So everybody is showing +3 oxidation state, some elements only +2 and +4. But here in actinoids, so these are showing +2, +3, +4, +5, +6, +7. So these are showing +2 to +7 oxidation states. Next, if you see the properties means these are similar to D block elements only. So complex formation. See, complex formation, complex compound formation is depending on oxidation state. That to be highest oxidation states. So here oxidation state is very less. So that's why less complex compounds. These are forming less complex compounds. Here oxidation states are very high. Oxidation state increases means complex compound formation. Complex compound formation is highest because of higher oxidation states. See, D block elements are showing complex compounds. Why they are showing highest oxidation state? Here actinides also highest oxidation states. That's why complex compound formation is more. Next, these are forming a lanthanide contraction. So here important, this is showing lanthanide contraction. So already it is available in your first year chemical bonding chapter and oxidation states also it is coming. Lanthanide contraction takes place. So because of for poor shielding of 4F orbital. If one word answer they are asking means simply you write poor shielding of 4F orbital. See, what is actually lanthanide contraction? I will explain briefly, just you observe here. So this electronic configuration is what? Nucleus is there. So general electronic configuration 4F14 maximum. Next 5D 0 to 1, 6S2. So after filling the 6S2 electron, the electrons are entering to 4F. So inside electrons are coming. So that's why these are called as inner orbital complex. So 1, 2, 3, 4, 5, 6. So this is 6S2. Here 5D, here 4F. So here after filling 6S, the electron enters into 4F. See here, compared to 6th orbit, 4f size is small. So size is small. How many maximum electrons? You can fill 14 electrons. So in the 4f, so smallest size, more number of electrons you are arranging means they are come close to each other. Suppose these two electrons, outside how many electrons are there? Inside also same number of protons are there. So this attraction only we called as a shielding. So within the smallest size, more number of electrons are arranged means electrons are arranged closely. 14 electrons are arranged. In what way? Very closely. They are arranged closely. That means they have repulsions are happened. Close arrangement is there means negative repulsion is happened. So that's why the nuclear charge is suddenly going outside. Who is outside? Here 6s2 electrons are there. So that's why because of this repulsion, the nuclear charge is going outside. And it is taken 6s2 electrons towards inside. Generally, group increases means the size is increases. Our expectation increment is not available. So it is decreases. Here 2 electrons are not coming outside easily. They are going inside. So that is also called as the inert pair effect. So simply here this concept you called as Lanthanide contraction. Here also we are getting actinide contraction. Here also actinide contraction is available. So because of what here? Poor shielding of 4f orbital. Here poor shielding of 5f orbitals. So one more orbit you increase. So that is it. Next, actinide. Actinide contraction is more powerful. Actinide contraction is more powerful than lanthanide contraction. So because of what? Inside the actinides only lanthanides are there. Lanthanides completion after only you are getting actinides. So that's why inside both contractions are there. Here F block, that lanthanides has only lanthanide contraction. So that is one important. Next, lanthanides are somewhat stable elements, but these are radioactive elements. These are radioactive elements. Then these are rare earth elements. So generally stable is there, it is available in sand. So the seaside sand it is available. So rarely available on earth sand. So that's why rare earth elements. Here after uranium. So we called as transuranic. Already we have completed once again. Transuranic, otherwise man-made elements. So similarly, D block elements type also. What are D block element properties? These are forming catalyst. Catalytic property also it is coming. Next, mixing of metals. Alloys also they are forming. Next, so there is melting of boiling points, that complex compounds, everything. Complex compounds also forming. So D block element properties, what they are showing, F also they are showing the same, but less compared to D block. See, what the D block elements are showing, the same property shown by F block also, but these are very small compared to the D. So these are the main important of F block.